So now we have already talked about the processing of the proteins in the ER. Now let's talk about that how these proteins which are already processed in the ER is transported into the Golgi, and what are the different things that actually happens in the Golgi. So before we start this process, one of the important things that you have to remember that there are two categories of the protein, and one is a complex protein and another is what we call as a high mannose protein. And we are mainly going to talk about these complex protein and not talk much about the high mannose protein, because this is more common than what we see in over the process. So let's take a look at that, what we basically mean by this. So if we just think about that a protein which is being transported, and we know that how the proteins are. So here you have the point where you have the ASN or the N, and then you have an X, then you have a serine threonine, and in here you have the attached moiety, which is the first two, as we know that this is your GLCN and the GLCN, and we have now basically 1, 2, 3, 4, then 5, 6, 7, 8. I mean, like, this is just only, this is not particularly the order that basically what it is. It is just a representation that there are 8 mannose in this process. That is all. They could be bonded in many different ways. So now, if we just have this high mannose, this is what we get from the ER. So this is what we got from the ER. Now this is transported into the Golgi. So right here, this is the territory of the Golgi, and it will be transported from chamber to chamber, one of them to the other, and all the compartments from the cis face of the Golgi. This is the cis face, and right here, if we just draw that, this will be the trans face of the Golgi. Each of the compartments will basically do different types of modification. So what are these modification? So the first modification that is done is the three mannose right here. 3 mannose will be removed by what is called as the Golgi alpha manosidase. So 3 mannose will be essentially removed. And once this is removed, after that, there be one protein which we called as the GLCN N-acetylglucosamine phosphotransferase. Not phospho, I'm sorry. The GLCN transferase, not phospho. This is nothing to do with phosphorylation. Is transferase. So what it's going to bring, it's going to bring in one of these GLCN in here. And I will just draw it down that how it will look like, GLCN right here. So this is basically the process which is going to happen. So this is your number 1 phenomenon, this is your number 1 phenomenon. At this time, when this is basically done with addition, removal, this is removal, and this is addition. Once this is done, the Golgi pretty much at this point is at the medial Golgi right here, at the medial Golgi. Pretty much, if this is the thing, it's in the middle. So it's moving that way. So now what's going to happen, that after that, there is another 2 enzymes that is going to work here. So here we have these Golgi alpha manosidase, and here also again there are protein which are Golgi manosidase 1 and 2. Here it was done by the manosidase 1. But here you are seeing that the Golgi manosidase 1 and 2. And what's going to happen, that it will remove again 2 mannose. So you can see that there are several things. You are removing mannose here, then you are adding an acetylglucosamine, and then here also you have the removal of these mannose. So now the glycosylation pattern of the protein is pretty much ready to be added with what we called, this is very important, as the complex moiety. So the complex moiety. And what are these complex moieties? These complex moieties could be addition of 2N-acetyl GLCN, 2N-acetylglucosamine. Then we have 3 galactose, and 3 sialic acid, which is also known as the NANA or NA, which is N-acetylnuraminic acid. So these are the 3 modifications that you are going to see. So ultimately, what it will look like in each stage that we are going to draw here. So let's take a look at each step, that how it will look like. So let's take this part off. So this will not be in the ER. This will be the step-by-step in the process, which will be 1, 2, then 3, and then 4. These 4 steps, how it's going to look like in each step. Let's take a look at that. So I'm just keeping this because you have 2N-acetylglucosamine that is attached. And now you have 8 from ER, what you had, and we are only talking about the complex here, remember that. So from the ER, you have 8 mannose was attached to this, and the first thing, the Golgi mannose basically removed 3 of them. So you have here, you have 1, 2, 3, 4, and 5 mannose. 5 mannose left on this. So now what you have, we have added in the step 2, 1 N-acetylglucosamine. We have added back again 1 GLCN, N-acetylglucosamine. So basically what happens in this process, let's draw it in a little bit different way so that we can draw them in a little bit nicer way. So right here, you can easily see right here, we can just draw this as, this is basically 1, then you have 2, then you have 3, and 4 and 5. So 1, 2, 3, 4, 5. All right. So we have this 1, 2, 3, 4, 5 mannose. Right here, 5 mannose. So we have added 1 GLCN. So we have added 1 GLCN right here. And then what we have, that step by step, Golgi mannose 1 and 2 will remove 2 of the mannose. So this mannose is gone, this mannose is gone. It will be left with 3 mannose, 1, 2, and 3 after this step. So which is basically this structure with 3 mannose. This is what I said is basically the basic structure that how your complex sugar will be. So how the complex sugars are attached to those, just remember that you have already right here, you have GLCN. So first you are going to attach 2 galactose, to galactose in there. On top of the galactose, so and a galactose right here. Sorry, no, hold on 1 second. In this step, you are going to add another 2 GLCN here. GLCN. You have added 1 N-acetylglucosamine before the medial Golgi, and you have added 2 of them which were empty. These 2 were empty, so you have 3 GLCN, 3 into GLCN. On top of that, what you are going to add, the second part will be the galactose. So you have the 3 galactose, 3 into the galactose, will be added next. So these will be the galactose. On top of that, you will have the 3 sialic acids. So these will be the 3 sialic acids. So that is basically the structure of your complex modification of your protein. You have 2 N-acetylglucosamine followed by 3 mannose, and to each of the mannose you will have 1 N-acetylglucosamine followed by the 1 galactose followed by 1 sialic acid. Each one of them will have that, and this is basically your complex sugar. Now, very interestingly, when this sugar pathway, which is the complex sugar, passing the medial Golgi, we actually can say. So what happens that up to this and this, there is a very interesting way that we can use some of these enzymes. That one of them is endo-H, endo-H, and that stands for endo-H glycosidase. So once you have this endo-H glycosidase, the region that these structures are susceptible to glycosidase and resistant to glycosidase actually varies. So what you're going to see that right here, this is from where this is susceptible to endo-H. So before these 2 mannoses are taken out, this structure is going to get digested by the endo-H. But as soon as this crosses the medial Golgi and alpha mannose 1 and 2 remove these 2 mannose, at this time what's going to happen, and of course the complex protein, this will be resistant to endo-H. And that's how what we can do, that if we are looking at the trafficking through the Golgi of glycosylation of a protein, we can take time points and we can just run them in a gel and measure the glycosylation pattern based on their molecular weight, because here you will have a molecular weight when they are taken off these two mannose, the molecular weight will get reduced, and we can actually tell that when they can get degraded or not. So basically what happens that at this point the endoglycosidase H is going to remove the glycosylation. So the protein molecular weight, if we just drawing in a gel simply, the protein molecular weight is going to show up as a lighter because you have it is susceptible and the glycosylation is taken out. Once these 2 mannoses are taken out and it will be resistant to the endo-H, your molecular weight will be up because the carbohydrate moiety is not going to be digested by the endo-H. So difference in this can be identified, or the transportation of the glycosylation of a protein where it crosses the medial Golgi can be pinpointed by this experiment. On the other hand, which high mannose, on the other hand, actually do not have a modification of the N-acetylglucosamine, galactose, and the sialic acid. They are just rich in high mannose. And for those, we actually cannot study them, but we can identify which one is a complex and which one is a high mannose sugar. So here you can see that right here is a complex sugar and here is a high mannose sugar. So what's going to happen that you can easily see that if you take a complex sugar which is completely modified, and we call this as a mature protein ready to go. That protein in the complex form, after it is synthesized, its molecular weight is somewhere here. On the other hand, what's going to happen, so let's do it in two different gel right here. So let's do this way. That will make a little bit more sense. So here you have before medial Golgi complex, and this is after medial Golgi. And the gel pattern will look like this. Before the medial Golgi, the molecular weight is less. because it was susceptible to endo-H, and after that it will be like this. On the other hand, if I just run a gel of high mannose like this, it's going to be the same. So this is before medial Golgi, and this is after medial Golgi. Both cases, it will be digestible by the endo-H. So the important part is that high mannose without any complication of these is always digestible by endo-H, or always susceptible of the endo-H. Doesn't matter whether it passed Golgi or not. So you cannot actually study trafficking of high mannose when it crossed the medial Golgi. You can only do that with the complex. On the other hand, how you can distinguish whether a protein is high mannose or complex? You get the mature protein. Basically, you wait sufficient amount of time where you see the protein has completely crossed the Golgi and it's in the vesicle, it crossed its the trans phase. You isolate the two proteins and then you digest them and compare them what they were before and after. If you see that there is no change in the molecular weight of a protein, every time it is being digested, always being digested by the endo-H, you know that is a high mannose. On the other hand, if you see that there is a change of molecular weight of the initial protein and the mature protein, you know it's a complex, because initially it was susceptible and after it got matured, it got resistance to endo-H. And this is how you can basically understand the complex protein transport through the Golgi and its processing.